Normally, it's a Stewart Island here. And Auckland is the largest city. It's 1/3 of the population of New Zealand basically lives in Auckland. New Zealand is a small country, about 5.6, 5.7 million people. Auckland, we have about 1.7 million people. So that's about a little bit about where I live. I've been in New Zealand now more than 22 years. A bit about our university. Basically, University of Auckland, I work here. University of Auckland was established back in 1883. And in New Zealand, we have the indigenous people, Maori. Some of you probably know. So Maori name of University of Auckland is students, and it's not bad. It's 68 in the according to QS ranking. This is our Faculty of Engineering building. This is a new building actually, which was it was done about couple of years back only during the COVID time. So I work at Civil and Environmental Engineering as a professor, and this is quite a big department. In fact, the Faculty of Engineering is the largest department, largest faculty in our university, and our department is the largest. So we've got 6 different groups: geotechnical engineering, we've got environmental engineering, which I'm part of, water resources engineering, structural engineering, construction, transportation, and civil engineering is highly ranked, ranked nearly 39th in the world. I do different things. My work is pretty much multidisciplinary. I work in different areas. So title of, my talk, as I said, I'm going to talk about biochar. So just to give you a bit of, drivers and motivation, why particularly we need to work on this topic. I'll tell you how we can apply biochar for different application, whether it is for remediating a contaminant from water, just like an activated carbon to purify water or to remove different contaminants. I have also used biochar for construction and building sectors. I'll talk about that, how you can use construction and building sectors, use biochar there. Then we have also used in geotechnical sectors, transport sectors, and other uses. There are so many different types of uses one can think of about biochar, because biochar is nothing but just carbon, as I'm going to tell you. And a bit of summary and the way forward. So some of the drivers are that, we are surrounded by, whether it's a developing country or developed country, it doesn't matter. We have huge amounts of organic waste that every day goes to landfill. A lot of regulatory bodies, they have basically put a lot of pressure, tight control and measures. And New Zealand also have got a zero waste policy. And of course, you want to dispose your organic waste in a sustainable and safe manner. Another thing is, how do you convert waste into gold? Basically, waste you convert into resource. That resource can be used or utilized in a way that it can be applicable for different sectors. And of course, you have the climate change, global warming. I think this is not a no-brainer. Everybody knows about the world is warming up. Things are changing. We have catastrophic, cyclone, flood, riverbed rising, seashores, getting inundated. So all those things, and also one last thing is the sustainability and circular economy, which we often talk about. We need to forget about going from linear economy, where basically we use the stuff and we just throw it. That's it. Once you use it and you throw it. That's linear economy. Circular economy, how you can make use of the waste or recycle the stuff that we have already used. So these are some of the drivers for my work, research work that I'm doing in New Zealand. So if I put you this slide here, you probably know what I'm talking about. Emission is a big issue all over the world, okay? Now, this emission not only from, industry, you're talking about cement factory, different types of industries in developed world, developing countries as well. This can create a lot of problem for our atmosphere, right? Global warming is a huge issue everywhere, and climate change is a huge issue. So we need to really be thinking about how to actually mitigate climate change, or how to reduce the global warming. Now, I have some black stuff here on my hand. This is nothing but charcoal, like your average charcoal. Now, when you talk about charcoal, how do you make charcoal? You basically burn a piece of wood, incomplete combustion of wood basically would give you charcoal. Now, this particular charcoal is something different because this particular charcoal is a charcoal that we have known about since ancient times. I'll talk a little bit about how the biochar history, how it started in the Amazonian basin in South America. So before that, I just wanted to give you a bit of, definition, if you like. But when I say definition of a particular terminology, that can be many. You find out a book, textbook, or any other journal article. Different people have defined biochar in a different way. Now, this is what I think often my colleagues and I use. Biochar is basically a carbon-rich byproduct that you get when you basically different types of biomass when you heat in the absence of oxygen or under limited amount of oxygen. And then because of the thermal degradation, you can get some syngas, carbon, like methane, hydrogen, propane, butane, ethane. You can get the solid material that is the biochar, and you can also get some oil depending on the type of biomass. So that's your biochar. So you can have different definitions. It's basically carbonaceous material that you produce in the absence of oxygen or under limited amount of oxygen, and then you convert that biomass into charcoal. So the difference between the normal charcoal and the biochar is charcoal is prepared with oxygen, okay? You need oxygen to burn. So biochar you produce in the absence of oxygen. But that actually gives you different properties. The properties of biochar that you produce different biomass would be dependent on the origin of the biomass. So it is very important that we need to understand the properties of the biochar before you can actually apply that for a particular application. Now, this is what, I don't know, I think many of you probably have already read. One of my colleagues, Johannes Lehmann from Cornell University, in 2007, he published a paper in Nature. I mean, under normal circumstances, what happens, plants basically absorb carbon dioxide from the atmosphere. And, so that, then in the process, with the process of photosynthesis, with sunlight, it just converts them into useful, nutrients and other things that you need for the structural components to grow. And then when the plants die, everything falls onto the ground. So that is basically, carbon sequestration if you talk about, by photosynthesis process. So this is like a 50-50 carbon neutral, because net carbon withdrawal from the atmosphere is basically zero. But on the other hand, if you pyrolyze the biomass and then convert them into bioenergy, okay, and then some of the biochar can be you can put back into the soil. So basically, you're placing the carbon back into the soil. So this is carbon negative because it will reduce the emission from the biomass. And at the same time, you will get certain percentage depending on the type of pyrolysis conditions you use, what kind of pyrolysis method you use. You can get bioenergy because that will give you emission reduction from fossil fuel. So that way, you can see 25% going up. So in this case, net carbon withdrawal from the atmosphere is 20%. So this is the normal circumstances, okay? Normal circumstances, you get carbon sequestration by photosynthesis, and biochar sequestration basically is a carbon negative technology. So this was published in 2007 in Nature, and Johannes Lehmann and his group, they have done significant amount of work using biochar as a soil amendment and also for other work. Now, this is just to give you a bit of background about how it started. Now, thousands of years ago, like, this is South America, this is the Amazon basin. So there was a discovery of Terra Preta do Indio. This is in Portuguese. In English, if you translate, this is called dark earth, black soil, basically, in Brazil. Now, this is the Terra Preta sites, people, the scientists, they dug up, they could find Terra Preta sites. Now, these soils basically contain high amounts of organic carbon, even after several thousands years after they were basically abandoned. Now, scientists have done radiocarbon dating, and they found that these soils were actually formed about 7,500, years, before pre-Columbian time. So if you're talking about 1 hectare-meter deep terra preta, okay, 1 hectare-meter deep, 1 hectare is what? 10,000 square meters, 100 by 100, right? That can actually contain your 250 tons of carbon, as opposed to normally that you see, that you see in unimproved soil, which will be about 100 ton, 250 ton in 1 hectare of terra preta. But under normal circumstances, if it is the soil is not improved, degraded soil, you could say about 100 tons. So Brazilian Amazonian Indians already use biochar long time back. And now people started to look at scientists, they took soil samples from there, they looked at the, amount of organic carbon level, and those organic carbons were very, very high, and they were recalcitrant. That means the carbon that is present in biochar is very stable. If you put biochar in the soil, it can stay for hundreds and thousands of years, okay? So that is one of the important properties of biochar. So this is another slide. Here, this is Terra preta de Indio. This is a soil profile in a normal soil, oxysoils in Brazil. And this is a soil very close to this particular area. And this is Amazonian dark earth. You see this here, very dark, very rich in organic matter, nutrients, etc. So this is highly fertile as compared to the parent material of normal soil. This contains nearly 70% of carbon as black carbon. And there were some studies done, field trials. They found in adjacent soil, they grew maize. And this is the maize grown in this particular type of soil or area, plot of land. And this is what you get when they found out that when they completed the trial, the Amazonian dark earth, they had significant amount of, production, maize productions. So these are some of the, a lot of things are already available in the internet. And this is another site, Terra preta do Indio in Brazil. This is a network of road that connects different villages in virgin forest. This is basically a graphical reconstruction of the Amazonian indigenous village. And this is just the same diagram that I showed you before. So anyway, now the question is, why biochar research? Now, as I said before, biochar is a carbon negative approach, because what you're doing here, you're utilizing the biomass, not just simply allowing it to decompose and create all sorts of emission issue. You're converting them into useful charcoal, and that charcoal have got certain properties which make them easily applicable for a lot of different things, like soil amendment, or as a contaminant remediation, or you could also do some other wonderful stuff, which I'm going to talk about. So one important issue here, we can get 2 benefits actually. You can get economic benefits as well as environmental benefits to tackle 2 major global issues. One is, it's not a problem. You have to either send it to landfill, and if you know what to do with the waste, convert that waste into useful product, that will have some environmental benefit as well as economic benefits. One is the climate change. Another one is the need for sustainable land management. And also, you can also use biochar as an effective engineered material to remove contaminant, for removal of contaminant. So how is biochar made? I don't have to probably tell you. I think all of you probably know, or some of you have already done work. There are different ways you can produce. There's slow pyrolysis, fast pyrolysis, there is flash pyrolysis, and there is also hydrothermal carbonization, which is slightly different. I'll tell you a little bit. Now, slow pyrolysis is very traditional way of producing biochar. We basically allow the biomass to go through the cylinder. That cylinder is being heated. You basically take the oxygen out of the cylinder, or as much as oxygen you can take out. You cannot completely make the reactor oxygen free. So you get pretty dirty, low char yield. You don't get a lot of yield for the char. And nowadays they have modern one where you can get high char yield. When you do slow pyrolysis, in the properties of the biochar that you get, as opposed to fast pyrolysis, they are totally different. I'll talk about it a little bit later. So there are different ways you can do. We normally use slow pyrolysis, where you basically hold the biomass inside the reactor for a longer period of time. And as you heat it, syngas will come out that you can capture to look at the energy value. You can get the solid charcoal. You can get also oil. But if you do fast pyrolysis, the reaction time is very, very small. Okay, you just hold the biomass inside the reactor for a short period of time. So the purpose of fast pyrolysis is mostly bio-oil production, not char. You can get some char, but mostly for bio-oil production. But you want to get more charcoal, more biochar, you want to go for slow pyrolysis. Okay, that again depends on temperature. Normally, we're talking about, say, 350 degrees Celsius where torrefication takes place. We have done 450, 550, 650, 750, 850. So as you increase the temperature, the properties of the biochar would also change. You know, there are certain properties of biochar which are extremely important to know beforehand, before you begin to think about, okay, I've got my biochar, where I'm going to apply. But first, you need to think about the properties. What kind of properties do you have? Or do you know the properties that you want that you're going to get once you make the biochar? So that is important. Other thing is hydrochar. Hydrochar is not actually biochar. For biochar, you want to have the biomass pretty dry, maybe 25, 26% water content. For hydrothermal carbonization, you can basically carbonize the wet feedstock using, you put some water, and then at a very high pressure, you basically get char. So that is the difference between the hydrochar and the biochar. So now, just to give you, how we produce. Now, this is a paper we wrote a long time back. This was a project funded by Ministry for the Environment. This is our pyrolysis machine. Here you see the cylindrical auger inside, and then you can see the syngas coming out here. You see this one, the syngas you can collect, look at the energy values, and you also get the bio oil, and you can also get the biochar. So this is the hopper, and this is the same machine, basically, two different views. So what we did, we had lots of different feedstock or biomass we tried. We looked at chicken litter, sewage sludge, broiler litter, pine sawdust, dissolved air flotation sludge, pulp and paper mill effluent, and many more. Even sugarcane bagasse also we looked at. We looked at macadamia nut shell, orange peel, you name it, cabbage, like cabbage leaves. Often, when you buy cabbage in the supermarket, you tend to take out the big leaves from the cabbage and you throw it. We've done some work with that. We've got some interesting results. So this was a project funded by Ministry for the Environment. We basically converted these biomasses into biochar using temperature range of 450 to 750 degrees Celsius. Time the biomass was held inside this cylinder was about 20 to 40 minutes. Now, all those biochars we basically characterized. And it's important to characterize this biochar, because if you don't characterize, you don't know the properties. Now, where can you actually, biochar is highly porous, okay? It has got very high surface area. It can retain a lot of water. It can retain a lot of nutrients. It is not easily degraded by microbes. If you have some biochar, depending on how you produce, what biomass you use, you throw it in the soil, it can stay stable for many, many years. Under normal circumstance, what happens? Labile carbon is easily degraded. And carbon that is present in biochar is highly aromatic. So it can be used as a soil amendment or as a supplement to fertilizer, remediation of the contaminant for stormwater, different heavy metals you can remove, just like an activated carbon. You can use biochar for greenhouse and nutrient loss. We have done some work on biocomposites by using biochar as a filler for polymer, because synthetic is not good. So we want to reduce the use of synthetic material by using carbon that is produced from waste material. We also use biochar as building material. I'll talk a little bit about how you can use actually biochar as building material. Bioasphalt. To produce asphalt, you need bitumen. Now, that is carbon footprint of bitumen is very high. So what do you do? Can you use biochar as a binder and then we produce bioasphalt. You can increase the shear strength of the soil, to mitigate liquefaction, or if you want to stabilize slope, then you can have biochar added to soil that can increase the shear strength of soil. You can use biochar as a landfill cover material. You can even use as a 3D printing material. And also there are lots of other areas of biochar in electrical engineering field, like development of electromagnetic shielding, humidity sensor, sensory material, and so on and so forth. So this is what we call biochar bioscope. See, what I have written here, just if you keep your eyes here, this is remediation. Remediation of contaminants, pollutants from water or soil. Now, if you want to produce biochar for remediation of contaminant or purification of water, you want to make sure that biochar will have high surface area, because it will be very good adsorbent. If you want to develop biocomposites as a filler material, you want to have biochar high surface area, high carbon, and low ash content. If you simply want to use biochar for carbon sequestration, you want to make sure that it has got high carbon content. The ratio of hydrogen and carbon is very, very low. Oxygen and carbon ratio is very, very low. These H/C and O/C, these are basically elemental molar ratio of biochar. This is not the percentage of hydrogen or percentage of carbon. This is you have to take into account the atomic weight of biochar, atomic weight of the element, and then you can get the value for H/C and O/C. And if you plot a graph, which is called Van Crevelen diagram, H/C in y-axis, O/C is in x-axis, it will tell you how aromatic is the biochar. So they need to be stable. They need to have high carbon if you're going to use biochar for carbon sequestration. If you now, if you're going to use biochar for exchangeable cations like calcium, magnesium, sodium, potassium, all those exchangeable cations, can be very, very high in biochar. Biochar would have very good cation exchange capacity, which is extremely important for plant growth. Also, another important thing for biochar produce, it tends to be alkaline in nature. pH is very high. So we have found biochar with pH of about 10. Now, if you have acidic soil, you don't need to use lime. Farmers in New Zealand, they often use lime because New Zealand soils are acidic in nature. So to offset the use, so you can basically use biochar, because biochar has got high pH. So that can actually bring the soil level, acidic level of the soil a little bit high. So there are different ways you can use biochar. These are only few. There are 50 different, 60 different uses of biochar, because biochar is nothing but just a carbon material. And you can design your way. You want to use it for such and such thing. You want to make sure that, oh, I need to use my biochar for this purpose. Can I have the properties of this biochar? So that's the important thing. Okay, this is just that biochar contributes to soil, and what happens, if you have a tractor just spraying pesticide. If you add biochar here, there could be reduced N2O emission, nutrient uptake, change in soil pH, because if you add biochar, it can actually increase the pH of the soil, because biochar is alkaline. Also the heavy metal or nutrient substance. This is just a simple processes, schematic diagram of processes that biochar contributes to soil. This was a cover page of Advances in Agronomy, one American journal. We published a paper a long time back. Okay, let me now a little bit tell you a bit about contaminant remediation. Okay. Now, contaminant remediation is of biochar is one of the most studied aspects, if you like. Okay, you can use biochar as an activated carbon. When you produce biochar, it's not activated. You can physically activate it or chemically you can activate. There are different ways you can basically activate. So I'll talk a little bit. So we use biochar as a potentially effective sorbent for contaminant. One of my PhD students worked. We produce, as you can see, New Zealand has got a lot of pine forest. This is softwood, and we produce a lot of biochar. And then what we did, we basically made the biochar magnetic, so that even after using it, you can regenerate it, you can recover the material back. So let's look at the removal of sulfur methoxazole, which is an antibiotic, from aqueous solution. How we did, we basically did magnetic adsorbent. One of the things is that if you can make the biochar magnetic, with the magnetic properties, that will give you rapid, efficient contaminant removal from aqueous solution. It's quite inexpensive. You don't need to really spend a lot of money. It could be developed, and that can actually bind to environmental contaminants. It can be easily separated from solution using a magnetic. So you can see this biochar has got in water, in solution, and as soon as you put a magnet here, all the biochar in solution is basically attracted. So this biochar has got the property of magnets. Why? Because if it contains contaminants, you can actually recover the material back and you can reuse it. So it can easily be separated from solution using a magnetic separators. I mean, there are different ways you can do. You can do magnetic zeolites, magnetic chitosan beads, you can use polymer adsorbents, or even you can use magnetic activated carbon. Now, as I said, are very important for biochar. Biochar is highly porous, high surface area, depending on what kind of biomass you use, what kind of temperature you use. Often what we have found, if you increase the temperature in the pyrolysis condition, most of the functional groups that are present will disappear. In chemistry, probably you must have studied different functional groups like group, carbonyl group. These are all oxygen-containing acidic functional groups. Now, these functional groups play a big role in the removal of or purification of metals or other contaminants from water. So therefore, you want to make sure that your biochar is well. For example, here we had control, not magnetic biochar. Carbon percentage was 86%. But when we made the biochar magnetic, adding 25%, this is using, ion chloride we used, using a oxidative hydrolysis method, 50%, 75%, 100%, your carbon percent actually decreases. So which is not good, right? But the thing is that if you look at even the surface area, 297 square meter per gram for normal biochar. But your surface area decreases when you magnetize. So what's the fun? What's the point of making it magnetic? There is a point. Why? Because although your surface area has decreased, carbon content has decreased, the material has become highly magnetic. If you look at the saturation magnetization here, the Armstrong meter square per kilogram, normal biochar magnetic properties is very, very small. Saturation magnetization is extremely small, 0.3. But when you totally do 75, 59.4, even if you make it 100% magnetic, it can be 89.9. So it's a basically trade-off. And these are some of the scanning electron micrographs. I mean, scanning electron micrographs are extremely important because it gives you a structural morphology of the biochar. You can see the pores, and it just gives you a visualization of what's actually happening. So I'm not going to move into much into that. So this is a Jobson isotherm for the antibiotics in synthesized sorbent. Here you're seeing how much of the antibiotic is sorbed. And when it is in solution, you can see the biochar, which is magnetized 50%. It has got very high, not this is, I think, what is it? Let me just have a look. This is 0%, up to here. But as you can see, higher the magnetic percentage, 75% magnetic pine soda's biochar, your sorption is actually reducing, which is actually not good. But the thing is that your material is magnetic. That is why it is important to convert the material into magnetic. Now, this is another one, looking at how surface area can be plotted as a function of different percentages of Fe3O4, because influence of Fe3O4 on the surface area, and the radiation can be actually evaluated by just simply looking at. You see this blue, these bars are situated in bed surface area. So Brunner emitted surface area of the biochar, it is basically decreasing. However, the magnetization, saturation magnetization is actually increasing. So it's a trade-off. So this one, we basically looked at how we can study the influence of iron oxide on the surface area and saturated magnetism, and also on the pore volume. This is on the pore volume side. It's a bit technical here, not going to explain that. These are some of the work done by my PhD students. She looked at also tea waste. This is tea bag that you use. Once you drink, you need to basically throw it, right? So what we did, we basically developed a green approach by using biochar-supported magnetic nanocomposites from white tea waste. But why we use tea waste? Tea leaves are very high in active polyphenols, and also it has got some caffeine. Now, polyphenols that is present in tea waste are very powerful antioxidants, and it has got a lot of radical scavengers, free radical scavengers. It can also reduce ion precursor in different phases. So that is one of the reasons why actually we used. So this was done by one of my PhD students, Na Zhang. She looked at the removal of different types of heavy metals from aqueous solution using biochar produced from white tea residue. This is the way she basically used. She basically boiled the tea waste, dried it, extracted the tea waste. Then we did the pyrolysis in the lab, small amount, at a temperature of about 450, 550, 650 degrees Celsius. Then we added iron chloride, and then we got the biochar. Okay, so this then we use for adsorption studies to remove different types of heavy metals from solution. This is again the scanning electron micrograph characterization that you can see what's actually happening inside the biochar. If you look at the, here, what you can see basically, there was no obvious in this page, in this one actually, there was no obvious magnetic particles introduced. The co-precipitation method basically led very strong aggregation. So this was a study recently done, and this is quite unique. We are actually going to now trying to find it is possible to actually scale up. I'm not just going to talk about these slides. So let me tell you a little bit about how biochar can be used in mortar and concrete. Now, I don't know if you has a very high carbon footprint. Okay, global carbon dioxide emission. Carbon dioxide emission in cement industry is nearly 8%, 7 to 8%. When you produce cement, then you basically emit lots of issues, greenhouse gases. Now, if you can find some material that can be used as a replacement for cement, that is a win-win scenario for you, right? So what we did, we use poultry litter. This is a chicken litter, and we use basal dust, formic acid, and bentonite clay, and we just enhanced this poultry litter, and then we pyrolyzed, and then we got the biochar. Now this biochar is produced from poultry litter, and we use cement, we use sand, and of course you need water, and you get the concrete. Now we looked at the mechanical properties of the concrete. Now this is just a rationale why we need to do. As I said, current global atmospheric carbon dioxide is quite significant, 420 ppm. It is increasing every day, every month, every year. Global emissions increased from 2 billion tons of carbon dioxide in 1900 to more than 36 billion tons in 2018. I said repeatedly before, 8%, 7% of global carbon dioxide comes from cement industry. Okay, so if you can find a material that can be used as a replacement for cement, or at least partial replacement, and you produce concrete, that's a win-win scenario for you. Also, you have to remember another thing, a lot of people, they don't think about the sand. There is a sand mafia actually growing in many Asia, Southeast Asian countries, including in India. And excessive digging of sand can lead to massive soil erosion, degradation of coastal and river environment. Therefore, even if you can reduce the use of sand in the concrete by using biochar, that is again a win-win scenario for you. So there is a need for alternative materials. Basically, when you pyrolyze, you can get biochar and bio-oil. Torrefication, you can get torrefied wool, which we talked about it. So there's a potential to sequester nearly 4.8 gigaton of carbon per year if 10% of the whole world biomass is transformed into biochar and charcoal. The biochar has got potential to increase the energy efficiency of construction material also, okay? Because thermal conductivity can be actually reduced. If you can reduce thermal conductivity, if you can reduce the flammability of the material, then it is good. Because even if a building catches fire, damage may not be that much. So one of my PhD students, Sai Pranit, who is doing a postdoc right now in Michigan, he looked at how can you produce dense composites, which we call biochar cement mortar, with lower thermal conductivity, yet it will have very high strength or sufficient strength so that it can meet structural requirement while making the process energy efficient. And we found out biochar is actually tougher than cement and sand. We do technique called nano indentation, which where you basically apply a micronewton load and look at the displacement. And we found that biochar is tougher than cement and sand. I'm talking about the particles here. Biochar has got biochar is very light, so you need a huge volume. So it reduces the density, and biochar is low thermal conductive material. So these are the favorable properties of biochar that you can make use of when you actually produce mortar or concrete. It will enhance the toughness, reduce emission, it will reduce density, also it will improve your thermal conductivity. So what we did, we used poultry litter biochar, which was produced at 450 degrees Celsius by slow pyrolysis. This is scanning electron micrograph of poultry litter. And we mixed that with bentonite clay, formic acid, and basal dust to make it compatible as a building material. And then we also look at the particle size distribution here. So these are the biochar properties. The major chemical composition of biochar to determine by ICP-MS. Carbon, hydrogen, oxygen, sulfur contents are given. And we use a aromatic ratio of 0.051. That means lower this value, that means the material is highly stable. Then we did control, any experiment you want to do control. So we looked at plain cement mortar, cement to sand ratio, water to binder ratio, and we replaced sand partially with biochar. We had a 10% biochar, 20% biochar, 40% biochar instead of sand. Some of the sand, because to produce concrete, you need what? Three things: sand, cement, and water, and some aggregates, right? Now, what we did in this particular study, we actually replaced the sand with biochar. And then we designated that as control B10, B20, B40. And then we made some mortars, hardened mortars. And then we looked at mechanical tests, looked at the compressive strength, flexural strength. We looked at the durability. We did some microcomputer tomography analysis, looked at the carbon dioxide footprint, looked at the water absorption, looked at the density of the mortars, and also we looked at the thermal conductivity. So I'll give you some findings, what we actually got. Cube size were very small, 40 millimeter, 40 millimeter, 160 millimeter. So we had 3 samples. Now this is the flexural strength. Now as you can see, flexural strength actually increased 0%, 10%, 20%. But if you put significant amount of biochar, then it again decreases. But overall, you could see the highest observed flexural strength recorded was about 6.3 megapascal when we had 20% biochar, which is actually 26% higher than the control, which was a good thing. But however, when we did the compressive strength of the mortar, it wasn't that good, because as you added the biochar into the concrete mortar mix, actually your compressive strength significantly decreased. We looked at the bulk dry density. That was quite positive because dry density control was quite high, nearly 2 grams per cc or 2,000 kilogram per cubic meter bulk dry density. But as we had at 10%, 20%, 40%, you could see reduction in dry density. So which is actually good. We also looked at the water absorption, how much water it can absorb the mortars and the voids. And we found that, with a different percent of the biochar addition, we could see that there's an increase in voids as well as in water. Other thing is important is often, looking at the thermal conductivity is extremely important, which is basically thermal conductivity or the effusivity you can calculate. Effusivity is basically a function of thermal conductivity, density of the material, and the heat capacity. I mean, we did this one using thermo test. Basically, this is thermal conductivity as a function of different percentage of biochar. As you can see, it is in control. As soon as we add biochar, the conductivity actually significantly decreased. But however, at 20% and 40%, having said that, if you just compare again, 10% and 20% still below the control. So which was quite positive. And these are some of the new area of research that our group has done. I don't think in Singapore, in National University of Singapore, they are doing quite a lot of work, but we actually initiated some of this work in New Zealand. Then we did X-ray microcomputed tomography. You can look at what actually happening inside the mortars. I'm not going to get into detail about X-ray microcomputer tomography. This is all about X-ray microcomputer tomography. This actually helps you to interpret or discuss your results. This is again electron micrograph energy dispersive X-ray analysis, looking at the different interfacial region between the cement, sand, and the biochar hydrogen product that is produced. So let me just tell you a little bit about this one, the environmental significance. So we wanted to find out, okay, we can use biochar in place of cement or sand. Does it tell us anything? How can you find out what is the net carbon dioxide emissions if we add biochar in the mortar or concrete? So what we did, we took an example. We assumed that we have 100 square meter area, 10 meter by 10 meter. It's like a big wall. It has got a standard thickness of about 1.2 centimeters or 12 millimeter thickness. It's basically a wall with 100 square meter area with thickness 12 millimeter, most mortar plastering. And we wanted to find out how we can calculate the carbon dioxide emission if you use biochar. Now, for cement, when you produce cement production will emit 1.002 kilogram of carbon dioxide. Just to get 1 kilogram of cement, you will be emitting more than 1 kilogram of carbon dioxide. For sand, it is significantly low. For biochar, it is carbon negative. So these are important attributes. Now, we found out that when you had biochar produced, a mortar that is produced at control, we had 508 kilogram of net carbon dioxide emission. But when you added biochar, 10%, 20%, 40%, there was steady decrease in net carbon dioxide emission. And this was kind of an empirical study, like a back of an envelope type of calculation. What we did, we used an Excel spreadsheet basically, and we calculated the values actually here. So this was quite interesting. Because if you look at here, this is control, cement, sand, and biochar, different parts of cement, sand, and biochar. See all these things are different. This is the density, quantity, and this is the carbon equivalent. And I would like you to keep your eyes on this because the carbon dioxide equivalent kilogram of carbon dioxide per kilogram, if you look at, it's quite negative, you see? So this is negative, biochar 0.49, for biochar 0.49. And if you look at the total carbon dioxide equivalent, for control, it was 494.7, okay? Control, but for B10, it is 494, 494, this is 494. But if you look at these values here, for the biochar, it is quite significant, right? It is minus 24, minus 48.72, and minus 97.44. So this particular work has got some relevance to environment. So environmental significance or environmental implication is extremely important for any work that you do. Just because, things tend to work very well in the lab, you want to make sure that if you extrapolate your lab studies to field studies, or if you upscale it, is it going to work? Sometimes they don't work, because when you basically scale it up from lab scale to pilot to commercial scale, a lot of the parameters have to be optimized. And there comes the big problem. So that is why often I think environmental significance, people tend to not think about, excuse me, but it is quite important. Okay, I want to talk a little bit about how biochar can be used as a hydraulic barriers in landfills. Landfills are not good, but we don't have any choice. Even in developed world countries, in New Zealand, Australia, UK, US, everywhere we have got landfills, because landfill, we throw everything, all the hazardous substances, and if you can provide a good cover material for landfill, so that leaching of the contaminant does not occur. So that's a win-win scenario again. So biochar can be used as a hydraulic barrier for in landfill. We have done some work on that. A landfill cover should ideally have a medium with high water retention. I mean, when you want to make landfill cover, you want to make sure that you have high water retention ability, and it has got low hydraulic conductivity, so that when it rains heavily, it will prevent the rainfall basically getting into the hazardous waste layer. Because if it goes like that easily, it can also carry the contaminants with it. So can you use biochar as a landfill liner cover? So the interaction, we also looked at using plants. We grew plants in the lab, in the soil amended with biochar. So interaction between biochar and plant, as well as the effect of biochar aging, means how many months, how many years, what it could actually have the influence on the plant growth, or all the overall hydraulic properties, which are not quite clear in the literature. So our study basically looked at effects of grass growth, and the grass that we use is Cerodon dactylon. We basically had soil that was amended with biochar. Then we looked at the soil water retention properties. We looked at the associated hydraulic conductivity. And this study was done over a 2-year period. And this study was done in India with the Indian Institute of Technology in Guwahati in Assam, one of my colleagues there. So we published this work some time back. So it was quite interesting. So these are some of the soil cores that we collected, where we basically grew the grass, and then we did all sorts of measurements, and we looked at the shoot length with time, with biochar amended soil with grass, leaf area index, shoot length, and also we looked at dry root biomass, again, function of time. So this paper was published in Science of the Total Environment. We basically did a 2-year evaluation of hydraulic properties, how it can change if you add biochar in soil, biochar amended vegetated soil, for application in landfill cover. Also, other thing is, another aspect how biochar can be used is, when you have earthquake. I mean, New Zealand has got a lot of earthquake too. In India also we get earthquake, especially in Northeast India, where I come from. So during earthquake, what happens? Sometimes the pore water pressure in the soil can be very, very high. So you get water coming up to the surface of the land. So if you can increase the shear strength of the soil, then that will actually reduce the pore water pressure. So we did a small study by one of my PhD students from Chile in Santiago, Jesslyn Pardo. She looked at how we can improve the biochar, using biochar, the liquefaction resistance of sand. So this was quite an interesting study. This is again coming from improving the shear strength of the soil, and you can also use biochar to stabilize the slope, because it properties, it improve the shear strength. So this is in geotechnical area. This is just this was published in Geotechnic journal. Here it shows the mechanisms of improvement of geotechnical properties of sand. So what happens, biochar has got a lot of functional groups. You see all these different functional groups. Again, not all biochar will have these functional groups. How you produce the biochar, what kind of biochar you're producing, what kind of biomass you're using, what is the pyrolysis condition, what is the temperature, how long you hold the biomass inside the cylinder. All those things will determine the surface chemistry. Graphene core, all right? You know, this one, and these are different properties. That's a functional group. Now, biochar particle here, water molecule can be outside. And with time, what happens, there could be formation of structural arrangement of the water molecules. And eventually, it can become more and more water will be surrounded on the side of the biochar. Now, what happens here? Here, the interlocking mechanism with apparent cohesion. Sand particles coated with biochar dust. This is the biochar particles with thin layer. And this is the apparent cohesion here. And so what happens during shearing, capillary pressure becomes very, very high. So there will be pore water pressure, increase of excess pore water pressure, and water basically enters new pores. So this is just a basically mechanism of improvement in geotechnical properties of sand. We did a small, it was a PhD study. One of the aspects of PhD studies is to find out how biochar can be used to improve the strength of the sand that we use for this work. Okay, let me just give you a bit of a different idea. So you can see biochar can be used for a lot of different purposes. So you can use it for soil amendment in the agriculture to improve crop productivity, to mitigate nutrient loss getting into the groundwater, or you can use it as a carbon sequestration. You can use biochar as a supplement for cement or sand so that you can have green concrete or green brick if you like. You can make pavement material. You can use biochar for geotechnical purpose, as I showed you. You can develop biocomposites material by reducing the use of synthetic polymer. Anything synthetic is not good. So if you can reduce the synthetic material use by using a material that is produced from waste, that is a win-win scenario, and the sustainability aspect is also there. So anyway, now let me just give you a bit of idea about the comparison of the commercial cost of biochar with other adsorbents. Now this is the price of adsorbents, so many dollars, US dollar per kilogram. This is the biochar. This is lower price and high price, okay? Now, if you look at here, activated carbon is something like this. Resin is like this. Multi-well carbon nanotube. I don't know, some of you, I also do some work on carbon nanotubes, single well carbon nanotube or multi-well carbon nanotube. This is different commercial comparison of biochar with other adsorbents that are available right now. Now, another important thing to remember here, the regeneration of spent biochar. It is very important to recover the spent adsorbent because it's a big challenge actually, especially at field scale. Regeneration depends on several factors. Cost of regeneration, type of regeneration, biochar becomes important. So for total cost, you have to look at production cost, regeneration cost, and process loss cost. So how can you make the biochar-based system a resilient one? So biochar-based remediation system can be resilient by attaining inherent characteristic. You can have diversity of the system that will allow you to use different types of biomass, efficiency due to low cost. And the system can be only cohesive if you can utilize the waste that would otherwise go to fill, because then it will reduce the emission. You will not have the emission problem. And also there should be immense interconnectivity, and there should be market accessibility of product. If you produce biochar, but there is no market for biochar, then your all efforts are gone. So design and make marketing of biochar-based system may be actually subdued if you do not have immense interconnectivity. So therefore, encompassing the production of biochar should focus more on the properties, fundamental properties, and not just simply the target extrusion that we want to produce biochar and use it. But you have to look at the whole process of production, characterization, application, and also you have to look at the cost-benefit ratio. You're producing biochar, but how much is going to cost? What is the techno-economic analysis? All those things we must do. All right, I think I'll end my talk here. I just wanted to acknowledge some of the contribution of some of my students here and colleagues. And I'd like to thank you for listening. And I leave this slide. It's a beautiful shot in South Island in Queenstown, which is a favorite destination of me. We often go there during summer, winter, autumn, or spring. This is the Mount Cook National Park. This is Mount Cook, where Sir Edmund Hillary practiced his mountaineering skill before he went to conquer Mount Everest. So I thank you all. Thank you.
Okay.
Thank you, sir. It was really an eye-opening session. I hope everyone has enjoyed the session.
Yes.
Okay, sir. On behalf of the School of Agriculture, Science and Technology, I would really like to express my hearty vote of thanks to Professor Ajit, who spared his time from his busy schedule. Thank you, sir, for sharing your knowledge and experience working with biochar. It will help our student to build some knowledge on biochar, I hope. They are only graduate students, so they are learning. They are in learning phase, actually.
Yeah.
Thank you, Professor Sahadev Singh and Divya Prakash ma'am, for organizing the event. Thank you, all the faculty member of Agriculture Department who make this event successful. Lastly, I would like to thank all the students, all the participants for attending this event patiently. Thank you, everyone. Thank you, sir. We would like to invite you here in the university.
Sure, I'll come next.
Yeah. Personally and visit our university. Thank you, sir. Really, it was a great session. Thank you very much.
Yeah. Next time when I visit New Delhi, I'll come definitely.
Thank you, Ajit, and I hope we will have some kind of long-term collaboration between your university and our technology business incubation unit, which is working on biochar from agricultural waste.
So please let me know the person who is working on biochar, their contact details. I can write and I can send some information so that we can talk and discuss few things.
Yeah, because I have discussed with our vice chancellor, and then he has given his green signal to go ahead. Sure. And I'll get in touch with you. Thank you very much for accepting our invitation and sharing your research with all our students. Some of them are quite junior, but I hope they will learn how to make presentations.
Yeah. Sure.
And how to
Thank you very much.
Yeah. How to listen.
Thank you very much. Thank you very much for inviting. Yeah, pleasure.
And we will have a group photograph. So you stay on the screen, and all the students will come on the back, and then we will have a group photograph.
Yeah.
My colleague wants to know something.
Hello, sir. This is Tribara. Sir, as you have told that in landfills we can use this biochar. So is it going to affect on the deterioration of groundwater quality? It will deteriorate the groundwater quality, or like in terms of when there are solid waste disposal sites are there are so many toxic materials percolates in groundwater and that deteriorates quality. So
Yeah, I think biochar basically you can use as a landfill line cover material because the purpose of our work is to find out whether you can reduce the water entry. Because if there is a heavy storm events, what happens? You tend to see more infiltration of contaminants if the lining cover is not very good. So biochar having with highly porous, it has got high surface area, then it can actually retain some of the contaminant. It will not allow the contaminants to go through the profile, even if there is a heavy rain. I don't think that's actually going to do well for the groundwater. Groundwater quality will not be compromised.
Please, all of you come on the podium here. Ma'am, sir, आइए. एक काम करो, मनोज, इस कैमरे का एक बार स्क्रीनशॉट ले लीजिए. कैमरा लेकर थोड़ा आगे चले जाओ, और खड़े हो जाओ. आप वहीं चले.
दिखाए भी नहीं मनोज तो इसलिए मैं फोटो भी दिखा आपको दिन दिखाई ना. देखो नहीं दिखाई भाई. तो एल्बम में किसके फोटो है?
ओके जी, बाय. ओके जी, बाय. थैंक यू.
Okay, bye. Thank you.
वहाँ पे मैंने कहा यार मैडम बच्चे तो आपका है ना.